name's Michael. I'm here for you. I'll explain the process. I'll answer questions if you have them along the way. Give me a shout. I'll answer those for you. But we are off and running. Claire has started by collecting some glass out of our melting furnace. Fresh out of the furnace, that glass is 2,100 degrees Fahrenheit. That's about 1150 Celsius. Or for reference, the same temperature is lava. Just like lava glows bright orange, so does our glass. Keep a close eye on that glass. Air blows into the end of the pipe tracking area where that air is pressurized, it expands, and it pushes into the soft glass, forming a small bubble. Did you see that get a little bigger? Perfect. There's now a bubble in this glass about the size of a golf ball. Now this is only enough material to make something small, maybe a drinking cup or an ornament. I'm guessing you would all like to see something a little bigger, a little fancier. So we'll let this cool down, and as it cools, it will begin to solidify, it will become rigid, and then we can return to the furnace to get more glass. At 2,100 degrees, that glass is so runny, it can't support its own weight. So if we try to get a lot of material at once, it will just drip right off the end of the pipe and onto the floor. Now, as this cools, it's starting to get much darker, and that's because we are using blue glass. In fact, this piece will be the same color as the pumpkin when it's all finished. Now, you were all here, you probably just saw Jesse shoveling stuff into this furnace. That's the raw material that makes our glass. We call it batch. So we're filling this furnace. This furnace holds 1,000 pounds of glass. But we still need to do demonstrations for all of you. So we have our small furnace on the right side of the stage, and at the moment it has blue glass in it. So today we get to make blue things all day. That furnace holds about 120 pounds of glass. But if you look at our screens, I just started a short animation. This is what it looks like when we get glass out of the furnace. All of the glass sits in a ceramic bowl. We dip the pipe down into that glass and we turn to wind up the additional layers that we need. We call these layers gathers, and use that as a bit of a term of measurement. So before we start something, we might say, I'm going to make this a 2-gather bowl, or I'm going to make a 3-gather base. And that tells me that she's collecting glass 2 times or 3 times. And with every subsequent gather, we get substantially more material. We organize the fresh layer of glass using first a wooden scoop tool called a block. We keep these wooden tools in water all the time. That's why they don't catch on fire. When Claire takes this wooden scoop away, that's steam coming out of the tool, not smoke. The water turns to steam. The glass floats on that steam layer, and because of that, we're not contacting the wood directly, and we can use those wooden scoops for sometimes a couple of years before we have to replace them. We like to use fruit woods. They burn out slowly and evenly to cut a dense grain pattern. This tool, not wood, but it's sort of a wooden tool, I suppose. That tool is newspaper. About 7 to 10 sheets of newspaper. We take newspaper, we fold it up, soak that in water as well, and work similarly, but because it's soft and flexible, we can contour and shape glass with the back burner. Ooh, we have the puzzle section. There's a maze on the back. We'll use this for about a week. After a week, that newspaper that's wet just begins to tear and fall apart. Just mushy wet paper. So we fold up the new one and we start over. Optic bolts. They change the optic properties of the glass. This is not a finishing bolt. We don't come out with a completed bottle or a jar or anything like that. We just get this ribbed texture on the surface. Now, if you look at our TV screens, there's a secondary furnace. We call this the reheating furnace because that's what it does. It reheats our glass. But you can really see the peaks and valleys on the surface. You can really see the texture from that bolt. Now, Claire is taking this one step further. We can leave those ridges vertical on the surface. But she's using these shears not to cut the glass, but to pinch those ribs together. Hot glass will stick to other hot things. So when those ribs touch each other, they fuse together and they create a permanent bond. So as we continue to shape and inflate this, we'll keep that texture. So it's not an elegant analogy, but it looks a lot like a chain link fence when you first pinch those together. But we'll keep that texture in the finished form. Now, we'll start the inflation. This happens in steps and stages. Declare a tissue, just blow one time really hard through the pipe. She can blow this up bigger than a beach ball, thinner than cellophane. You can blow it up so big and so thin, you can actually pop the bubble, which is kind of cool to see. It's pretty interesting actually, but it makes for a very short demonstration. So we don't want to do that. But we'll inflate this little bits at a time, and then of course we'll work between the bench and the heating furnace. Because as we start inflating this, or making it thinner, or stretching it, that glass is going to start cooling faster and faster. So the working time begins to shorten. So we can look at how the glass flows. That of course tells us some of the story. The brighter orange it is, the hotter it is. And then as it cools, it gets darker. You know that it's not as hot. It's not going to move as much when we try to shake it. But we look more at how the glass is moving. That tells us more of the story. When we look inside of the bright orange reheating furnace, of course, everything looks orange. So we can't discern the temperature based on how the glass is flowing. So we look at how the glass moves. Now, this is also important because if we started with clear glass, we have a different way to add colors. And that's with something called frit. These are just little pieces, chips or shards of colored glass. So we can roll it clear, throw these little pieces, and then these pieces stick when we dump them in. And there are nearly 200 different colors to choose from. So this green glass, this looks orange when it's hot, but when orange glass is hot, it looks brown. When the red glass is hot, it looks almost black. So just looking at the glow isn't always the best way to tell. Now these different colors, they're made by adding different metals into the clear glass recipe. That green glass is made with this red stuff. This is iron oxide, essentially rust. It makes green glass. So because green glass is made with rust, and rust is fairly common, actually it's very common. I'm not sure how many of you are from the area. You've seen how much salt is put on the roads. A lot of rust around here. But that means that the green glass is fairly inexpensive. Pink glass, however, is made of gold. So that makes pink glass very expensive. But we're going to start adding some additional components to this piece. So Claire asked me to bring some glass over. This glass will fuse right onto the bottom of the bubble. The hot glass sticks other hot things. Remember, those ribs stick together. This glass will stick together as well. And she'll start to shape that up. Now, this is also great because I can show you about those thermal properties. That glass where it's thin, I can already touch it. Up here where it's glowing orange, it's still hot. If I grab this, I can pull and stretch it out. If my arms were longer, I can stretch it even more. But that's a nice way that I can illustrate those thermal properties, how quickly that thin glass cools down. So this is going to be the stem, so we will work together to finalize the shape of the stem. And Claire's making a little sphere in the center of this stem. So she'll use these steel tools, the jacks. She used these before. And I'm going to use a wooden pad. Anytime you use two tools together like this, we are essentially making a mold for the glass to fit into. So we can work together to make the profile of our stem. Now these jacks, they are a hand-made tool. I think that's interesting because it's a fairly niche market for hand-made glass blowing tools. So there are probably 4 or 5 tool makers that have a real stronghold on that tool market. But we have tools from tool makers in Italy, in Japan, here in the United States. And every glass maker has a preference for whose tools they like best and why. A pair of jacks like that can range from a couple $100 to a couple $1,000. It all depends on who made them. But we're going to add glass now for the foot of this piece. So just like before, I'll deliver some glass, we'll wind this on. And then Claire's going to use a tool to make the foot. We call this the footing tool. This footing tool is made with the same fruit wood like we use for those wooden scoops. But we squeeze the glass between these two boards. It's a really simply designed tool. just a nylon strap stapled on the two boards. When we squeeze the glass, it flattens out in between those two boards. Now this tool is tricky because if you don't have the correct amount of glass, if you are not turning at the correct speed, if you're not squeezing at the correct pressure, very easy to catch and bind to the glass in between those boards. So instead of making a beautiful round foot, like what Claire has made, you make something that looks more like a fried egg. We've all done that. So a simply designed tool, but a very tricky tool to use. Now Claire does make all of this look very easy. She's been working in class for, what is it, Claire, about 14 years? Yeah, about 14 years. So she has a lot of skill and a lot of experience. Now that foot, that's still really hot. So we're just going to balance out the temperatures of this piece. Use that torque. That's a propane torque. We focus in on the top section just so that we can equalize that temperature throughout. We are about to break the glass off of that blowpipe. So Claire created a constriction just off the end of the pipe, and she used those jack tools. So that line, we call it the jack line. But we like to compare it to the line in a chocolate bar. The line in chocolate tells chocolate where to break. The line in glass will help guide our glass with where to break as well. We do need a way to catch this piece though, so I'm going to create a temporary handle, which we call it just a small amount of glass. I'm shaping this on a steel table, and I'm importantly cooling this down. The stem and the foot, they were so hot when we attached them that those are permanently connected. But we want this to just be a temporary connection. So we want this to break free at the end, so we can't attach it too hot, but also if we don't attach it hot enough, then the piece will fall off before we want it to. So this is the Goldilocks moment. Everything has to be just right, not too hot, not too cold. So we place this right in the center of the foot. Claire will break this from the blowpipe using that jack line, as well as some thermal stress. A couple drops of water, or even at this point, just a room temperature steel tool will chill that glass so quickly, will create these little cracks and fractures. So one drop of water, a little tap, and that piece breaks right off perfectly. I say we give Claire a little round of applause for glass breaking. Now, I bet a lot of you have probably, you're welcome, broken glass before. You probably did not get a round of applause. But we like to celebrate that, because that's where a lot of things can go terribly wrong. And that's where a lot of things do go terribly wrong. No. Sometimes people think that if we inhale, something terrible will happen. We would be totally fine. By the time that air travels back through the pipe and gets to our mouth and our lungs, it's cooled off that it doesn't harm us in any way. There are actually techniques where we will breathe back in on purpose, which collapses the bubble, but it doesn't hurt us. So yeah, sometimes we will intentionally breathe in a little bit to change the shape of the bubble. But when you're trying to inflate it, if you breathe in, and you're just doing the opposite of your intentions. Yeah. Yes? Yeah, no gloves. Doesn't it get hot? Gloves actually impede our dexterity. They make it much harder for us to turn the pipe and use the tools. So the pipes that we do use are stainless steel, which as far as metals go, fairly poor conductor of heat. So I want you to see this, and then I'll go back to my visual reference. Where it cuts through the glass, just to thin and refine that top edge. But pretty cool, you can cut glass as long as it's hot, it's soft. But the stainless steel pipes, there's this visible tarnishing here. We don't touch this. We call this the hospital zone. We've all touched it. Probably only once or twice. I didn't learn a lesson. But the heat does not travel too far up these stainless steel pipes, so that's why we use the stainless. So yeah, we don't really wear gloves too often. We will on occasion if we're sculpting, if we're close to the glass for a prolonged period of time. We might, but for most of the things that we make, it's just not necessary. But we do wear cotton clothing, natural fibers, no synthetics that can melt to you if something were to land on you. Closed-toe shoes, eye protection. Otherwise, those are pretty much the rules. But I want to draw your attention back to Claire because she has a beautiful piece just as it sits. She's going to make this a little bigger and a little fancier. So if you watch closely, when this glass gets hot and soft, it will start to try to collapse. It'll get wiggly She'll prevent that just by turning faster and faster, and the faster she turns, the bigger it gets. And then when she holds this down, it folds and makes a beautiful fluted bowl. And that fluting is determined by the mold that she went into, the way that she pushed those ridges together, and of course by the way she distributed the material initially. So it makes a perfectly, even perfectly fluted bowl. That is the final shaping step. But there is one step left, and that's to save our bowl. So we'll put this into an oven to cool down slowly. That's a process that we call annealing. But one drop of water and another tap, that piece breaks right off. And then we will put this into our oven to cool slowly. Let's see if we can get a quick picture. Alright, and we'll take this away. Yeah, let's get this just below 1,000 degrees Fahrenheit. Everything that we make today goes into this oven, and then it will all cool down gradually together. So if we make something that's really thick, it has to cool down for longer. If we make something very thin, it can cool down faster. But we'll make pretty much everything the same thickness today, so it will cool for 8 hours. But if we made a bunch of thin things and then we put one thick thing in there, all of the thin things would still have to cool down for the length of time determined by the thickest object. But we'll see that tomorrow. Tomorrow, a nice big open bowl like that,